Hello everyone, welcome to this webinar series. Silicon carbide provides many advantages over silicon and industry adoption is growing fast. One common challenge to upgrade from silicon to silicon carbide is the noise and EMI induced by fast switching speed, which in the meantime enables high efficiency and high switching frequency. In this video, we're going to show you where our technology stands in the silicon carbide industry and share our recommendation to overcome the challenge of fast speed. First, we're going to introduce our Gen 4 750-volt silicon carbide FETs and their excellent performance. This technology not only provides the best figure of merits for silicon carbide devices, but also enables many other features such as 0 to 12 volt gate drive compatibility to silicon drivers, long short circuit withstand time, and low body diode forward voltage drop, and so on. Next, we will provide more details to explain the reason for superior performance. Our user guide, app notes, and webinars can help you exploit silicon carbide FETs benefits more easily and reliably. In the end, we will demonstrate the efficiency improvement enabled by silicon carbide FETs, which allows cost reduction from building materials and operation. United Silicon Carbide has been studying silicon carbide since 1999. Today, our product portfolio covers Schottky diode, normally on silicon carbide JFET, and normally off silicon carbide FETs. Our focus today is on the Gen 4 devices in the FET family. You can find the generation from the part number UJ4C. For the FET family, we make 650 volt, 750 volt, and 1200 volt devices in various discrete packages. We also provide the industry's lowest RDS sound for these packages. Main benefits and features are highlighted in the summary on the right. We will dive into these benefits in later slides. First, let's see where our technology stands among various technologies. As we know, silicon carbide is a wide bandgap material that has 10 times higher critical field for breakdown compared to silicon. We can design silicon carbide devices to have a much lower resistance per unit area, also known as RDSA, than silicon devices. Silicon carbide also has 3 times higher thermal conductivity than silicon, so the heat can be removed from the junction to case more easily and allow device to operate at higher current densities. The chart here shows the RDSA versus breakdown voltage limits of silicon and silicon carbide. As we can see, silicon carbide can handle 10 times higher breakdown voltage at the same level of RDSA. The dots represent various state-of-the-art technologies and where they stand in this map. The black stars are silicon superjunction devices. The gold ones are Gan devices. The black squares are state-of-the-art silicon carbide MOSFET, and the blue circles represent silicon carbide JFETs or FETs. And you can see we're in the front line to reach the limit of silicon carbide. This allows our device to have better figure of merits and enable compact and cost-effective power converters. The previous slide shows our technology provides lowest RDSA for a given breakdown voltage. As a result, we make the industry's lowest RDS on devices in a given package. This chart here shows the lowest RDS on devices we provide in a 2-47 compared to what other silicon carbide vendors provide in the same package. Using our technology, you need less devices in parallel to generate the same amount of conduction losses. This is of great value to improve efficiency and increase power density for EV motor drives. The radar plot here compares the overall performance of Gen 4 silicon carbide FETs versus other silicon carbide MOSFETs. We can see that the Gen 4 devices provide superior performance for almost all key parameters in hard switching and soft switching figure of merits, while providing extra margin at 750 volt. In this radar plot, the smaller the area, the better the performance. The highlighted blue circle is United SiC 750 volt Gen 4 silicon carbide FETs. The gray circles represent 650 volt silicon carbide MOSFETs from 4 different vendors. We have much lower on resistance per unit area at both room temperature and 125 degrees C to deliver the lowest conduction loss for a given die size. We have lowest forward voltage drop on body diode to deliver low daytime loss and relieve the demand for synchronous rectification in third-quadrant conduction. We also have lower hard and soft switching figure of merit to deliver lowest switching loss for both hard and soft switching applications. Please visit our website to discover more features of our Gen 4 silicon carbide FETs. Besides the great switching and conduction performance, the Gen 4 devices also delivers gate drive flexibility. All devices can be safely driven with standard 0 to 12 volt or 0 to 15 volt gate drive voltage. Good threshold noise margin is maintained with a true 5 volt threshold voltage. Like previous generations, these new silicon carbide FETs can be operated from all typical silicon IGBT, silicon MOSFET, and silicon carbide MOSFET drive voltages. The VGS rating is compatible with silicon devices with a range of positive to negative 20 volt. It also includes a built-in ESD gate protection clamp that limits maximum gate spike within positive to negative 25 volt. The industry's lowest on-resistance discrete will also come with an industry-best short circuit with stand time. In the figure here, you can see the short circuit current waveform of the new 6 milliohm 750 volt FET. When starting from 25 degrees C, the waveform is in gray. When starting from 175 degrees C, the waveform is in blue. The bus voltage is 400 volt. Even when starting from TJ max 175 degrees C, the device safely withstands more than 7 microseconds. The 5 microsecond rating will allow designers adequate time to safely detect and shut down a short circuit event. To help designers optimize power design across various power level and topologies, the 750 volt Gen 4 portfolio offers 13 discrete options. The lowest on-resistance products, the 6, 9, and 11 milliohm devices, will be offered in 2 to 47 4-lead packages, while the higher on-resistance parts with 23, 33, 44, and 58 milliohm devices will be offered in both 2 to 47 3-lead and 4-lead packages. With higher voltage margin at 750 volt and superior figures of merits, Gen 4 devices enable efficiency improvement, reliability improvement, and cost reduction for various applications including automotive, IT infrastructure, and renewables. We have introduced the excellent figure of merits of Gen 4 silicon carbide FETs to provide low conduction loss, low switching loss, flexible gate drive, and best short circuit with stand time. A lot of these features relies on the low RDSA of silicon carbide FETs. Next, we will dive into the device structure to explain why silicon carbide FETs has the lowest RDSA and other benefits enabled by this structure. Thank you very much for your attention. Please stay tuned for the next video.